So good morning all. So today we will discuss how to generate AM double sideband full carrier using switching modulator. Okay. The previous class we discussed how to generate AM using square law device or a square law modulator. Okay. Today we will discuss how to generate AM using switching modulator. So as part of this lecture, at the end of this lecture, what you will understand is how to use a switching modulator to generate AM double sideband full carrier. So what are the blocks involved to generate a switching modulator? So that is what we are going to study. So AM double sideband full carrier generation using switching modulator. So you might wonder, what is the switching modulator? So switching modulator is very simple. We are using the switching characteristics of diode to generate an AM full carrier. That is called switching modulator. Okay. So let me draw the diagram first and then explain you the operation of the circuit. The switching modulator consists of a diode. Okay, this is diode. And you know, for any modulation, you require two inputs. Okay, so what are the inputs? Message and carrier. Okay, so message and carrier. So this is my carrier signal. This is my message signal. This carrier is AC cos omega CT. Okay, so this is my carrier and M of T is my message. Okay, so this is given to a band pass so this is a band pass filter BPF. Okay, so it is a band pass filter with the center frequency with FC as center frequency and bandwidth as 2 times FM. So you should choose band pass filter such a way that the center frequency is FC and bandwidth is 2 FM. Why? Because it is a double sideband full carrier circuit. Okay, so you require both upper sideband, lower sideband. So whose bandwidth is 2 FM. You should have a center frequency tuned at FC. FC is nothing but carrier frequency. Okay. So this output is nothing but AM double sideband full carrier. Okay, or it is B AM of T. Okay, so let me say my input is VI of T. It is at the input side, at the input to my diode, my input is VI of T, and the output of the diode or the output to a bandpass filter, I'm saying it as V out of T. Okay, so VI of T and V out of T. So that is what. Okay, so my input is M of T and this is C of T. C of T is nothing but carrier. So this is C of T. Okay, so let me start deriving it. So before deriving this, I would like to give some intro on the diode switching characteristics. Let us see that. So you all know, by applying KVL to the input side, we get Vi of t as m of t plus AC cos omega ct. Correct or not? So what is VA of t? M of t plus AC cos omega ct. Okay. And okay. And diode. So you know that when a diode is forward biased, it acts as a short circuit. Okay. And when diode is reverse biased, it acts as an open circuit. Okay. This is for an ideal diode. Okay. So that is called switching characteristics. So we will use another property like for an ideal diode, when it is forward biased. Okay. So diode is on and it acts as an short circuit. And during the reverse bias, diode is off and it acts as the open circuit. Okay. So you know that VA of t is given as an input to the diode. See, VA of t is given as input to the diode input. So for a diode to be forward biased, the input should be what? Input should be positive. Input to the diode. Input is what here? VA of t. So VA of t should be positive. For your diode, VA of t should be positive. Okay. That is VA of t should be positive, and during reverse bias, VA of t will be negative. Okay. So this is the logic we will use to generate AM using switching modulator. So the logic is very simple. When the diode is forward biased, it acts as a short circuit, and this will happen when your input is positive, because forward bias will happen when input is positive, and reverse bias, diode will become off and it will act as an open circuit. Reverse bias will happen only during when your input is negative. Okay. See, we have discussed modulation index M is equal to Vm by Vc. Okay. And you know your M should be always less than 1 for perfect modulation. Okay. When it is greater than 1 or below that, you will not get perfect modulation. So M value should be in the range of 0.7 to 0.8. That is what ideal value of M. Okay. Now, for M value to be less than 1, definitely your Vc should be greater than Vm. Correct or not? Only then you will have value between 0 to 1. Okay. For instance, M is equal to Vm, let me take 2, and Vc, let me take 4. Okay, so Vm will be less than Vc or Vc will be greater than Vm. Okay, only then I will have my index between 0 to 1. Okay, so Vc is greater than Vm. That is the important condition you should know. Okay, so what is Vc? Vc is nothing but carrier peak voltage. Okay, so in this circuit, your VC is nothing but AC, correct? AC cos omega CT is nothing but your carrier. See here, AC cos omega CT is nothing but your carrier. So your carrier voltage should be higher than your message voltage. That is what my observation. Okay, so one important condition is your carrier voltage. Okay, AC is nothing but carrier voltage should be greater than your message M of t. Okay, that is one condition you should know. Okay, so now, so always your carrier signal is high when compared to message signal. For what? Only then you will have. So always we assume that carrier is dominating. Dominating means that is the polarity of VA of t is dependent on carrier. Okay, so this is very important point. The polarity of assume carrier is dominating, that is the polarity of VA of t, that is nothing but input to your diode. So polarity of VA of t is dependent on your carrier. So your input to your diode dependent on your polarity of VA of t. Whereas this VA of t is dependent on what further? On your carrier signal, that is AC. Okay. So let me, you know that VA of t is equal to M of t plus carrier. So let me write your carrier as C of t. Okay. So see, now I will take four different conditions. So let me take M of t as 0.5 and this as 5. So this VA of t is nothing but what? Input to diode. Okay. So if you see here, see, this is positive, this is also positive. Okay. This is negative, this is also negative. This is negative, this is also negative. This is positive, this is also positive. So what is your observation? So the observation here is the polarity of carrier decides the polarity of VA of t. VA of t is what? Diode input. Okay. So if your diode input is positive, your diode will be forward biased. If your diode input is negative, it will be reverse biased. Okay, so that is what. Okay, so what I'm trying to say is my polarity of my carrier decides the polarity of my diode. That is, if my carrier is positive, my input to diode is positive. Okay, if carrier is negative, that is carrier polarity. I'm just saying carrier polarity. Input to diode is negative. Okay, so that is our observation. So observation is if your carrier is positive, your diode input will be positive. If your carrier is negative, then diode input will be negative. So positive during, you know that carrier is a sinusoidal signal, AC cos omega ct. So sinusoidal signal will have positive half and negative half. So during your positive half of your carrier, your diode will be positive and it will be forward biased. During your negative half of your carrier, diode will be negative and it will be reverse biased. So that is the main important condition you should know. Okay. So positive half cycle of carrier, my diode is forward biased. Okay. During negative half cycle of the carrier, diode is reverse biased. So this is one important condition. Now let us see what is the output for forward biased and reverse biased. Okay. For positive carrier half cycle. So you know that for positive half, your diode is forward. So you know that VA of t is equal to positive. Because during a positive half cycle, your diode is forward biased. Okay, carrier, you know that VA of t polarity is dependent on carrier polarity. So the carrier polarity is positive. So definitely VA of t will also be positive. Okay, and when VA of t is positive, your diode input is positive. That means diode will become on. Okay, so diode will become on. So when diode becomes on, your see. So when diode becomes on, whatever is your input, that will come to your output. Correct or not? See, when diode is on, for example, this is your diode. So the input of your diode is VA of t and the output of your diode is V naught of t. So when diode is on, so what happens? When diode is on, it will become short circuit. So short circuit means this is short circuit. Okay, so short circuit. When diode is on, the diode becomes short circuit and your V naught of t is equal to VA of t. Okay, this is for positive carrier half cycle. Similarly, for negative carrier half cycle, so negative carrier half cycle means your input is negative. Okay, if my input is negative, my diode will be reverse biased. So diode reverse biased means diode will be in off condition. Okay, so in off condition, your diode will become open circuit. Okay, so this is VA of t and this is V naught of t. So on open circuit condition, there is no current flowing, so voltage will be 0. So your V naught of t is equal to 0. Okay, so that is what. So this is so the circuit is operant only on the diode switching characteristics. Okay, so the circuit is operating based on diode switching characteristics. So let me say this as equation 1 and this as equation 2. Okay. So now I'm trying to combine equation 1 and 2. So how can I combine? So V naught of t is equal to, I'm adding a term called P of t into VA of t. Okay. So that is during my positive half, during my positive half, VA of t is positive. So I can say P of t is equal to 1. So, okay. So if P of t is equal to 1, see, I'm rewriting this again. During positive half, during negative half. Okay. During positive half cycle, uh, P of t is equal to 1. Okay, during negative half cycle, P of t is equal to 0. So what if P of t is equal to 1, you will have V naught of t is equal to VA of t. And if P of t is equal to 0, you have V naught of t is equal to 0. So this is an important equation. Correct or not? This equation is very important. Okay, so combining 1 and 2, you have these two equations. So what is your observation? So during your positive half cycle of your carrier, your P of t is 1, and during your negative half cycle of your carrier, your P of t is 0. Okay. So what should be this waveform? 1, 0. What is that? See, that is during positive half, my P of t value should be 1, then it should be 0. So this is equivalent to what wave? Any guesses? There's none other than square wave. So P of t should be a periodic square wave, because during positive half cycle it should become 1, during negative half cycle it should become 0. So this is a periodic square wave, SQURA, square wave. Okay. See, and I said it is a periodic square wave, but what is governing all this? Everything is governed by your polarity of your carrier. So what should be your frequency of your wave, square wave? Frequency of your square wave is also governed by your carrier frequency. Okay, or if you write in terms of time period, it is carrier time period. So the frequency of your square wave is also governed by your carrier time period. The reason is carrier governs the switching characteristics of your diode. Clear? Okay, so now let me draw the square wave. Okay, so it's a periodic wave. Okay, so this is 0, this is P of t, and this is time period t. Okay, and this is Tc. This is minus Tc. So period of your square wave is given by Tc, and this is 0. Okay, see if this is Tc, and what is this half of this? This will be Tc by 2, correct? Then this will be minus Tc by 2. Okay, okay. If this is Tc by 2, then this will be what? Tc by 4. And this will be Tc by 4. See, the curve should be symmetric, but my drawing doesn't appear so. Okay, sorry for that. So Tc by 4. And if you calculate this time period, upper limit is Tc by 4, lower limit is, this is minus. Lower limit is minus Tc by 4. So what is your period? Period is Tc by 2. Okay, and this is Tc by 2. And what will be this value? This will be also Tc by 2. Okay, that is, this will be 3 T, I mean 1 by 2. So this will be 3 Tc by, see, this is 1 by 4, quarter, half, then this will be 3 by 4, correct or not? So 3 Tc by 4 minus Tc by 4 is 2 Tc by 4. So what is 2 Tc by 4? Tc by 2. Okay, so actually this width should be equal to this width, but because of my diagram it looks so. Definitely it will be equal because this is a periodic square wave. Okay, so this is what. So you know that P of t is a periodic signal. Okay, and you know that Vi of t, sorry, V naught of t is equal to P of t from the previous derivation, P of t into Va of t. So you know Va of t. What is Va of t? Va of t is nothing but M of t plus C of t. We have derived it earlier. Okay. Okay. But P of t. See, P of t, you have a periodic wave. So how will you find the expansion of a periodic wave? We have learned this. So the correct procedure to find the time domain expression for a periodic signal. What is the technique called? Fourier series expansion. So we will use Fourier series expansion to find the time domain waveform P of t. Okay, that is the final equation, synthesis equation. So you have analysis equation and synthesis equation in Fourier series. In that, we are taking the synthesis equation. Okay, so synthesis equation, your equation will be in form of t. Okay, your analysis equation will be in form of a naught ak Fourier series. So synthesis equation we are taking it and we are using it directly. See, this is a square wave. So I'm not. We have learned this in signals and system, and we have derived it in signals and system. So what I'm doing is I'm not going to derive the Fourier series expansion of square wave. Instead, I'm writing the final expression, assuming that you know how to derive it. Okay. Okay. So P of t is given as square wave representation of Fourier series, correct? So let me write the equation alone. See, so definitely your P of t. So definitely your P of t will take this form. So I'm just writing the final expression. This is my Fourier series representation. So see, there are infinite terms. So for ease of understanding, I will take only two terms, 1 and 2. Okay. So if I take n is equal to 1 and 2, if I substitute, I will have P of t as 1 by 2 plus 2 divided by pi into minus 1 to the power 0. So anything divided by 2 minus 1. So you'll have 1 by 2 sorry 2 minus, sorry, it is 1 by 1. Sorry, I made a mistake. 1 by 6 because n is equal to 1. So 2n is 2 minus 1 is 1. 1 by 1 cos of 2n. So what is n is equal to 1? So it will become cos omega ct. I am writing 2 pi f as 2 pi fc as omega c. So 1 omega ct. And if you substitute n is equal to 2, you will have cos n is equal to 2. So cos 3 omega ct. Okay. See, even if you're not able to remember this expression, remember this expression at least. This is sufficient for switching modulator because you cannot derive it and you can solve because it will be very difficult if you are deriving your Fourier series expansion of a square wave, and if you're solving it, this derivation will be very cumbersome, it will be very big. So remember this expression alone for your exam purpose. Okay. So this is what P of t is equal to 1 by 2 plus 2 by pi into 1 cos omega ct minus 1 by 3 cos 3 omega ct. Okay. 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 So cos omega ct. So this is my expansion for Fourier series. Okay. Fourier series expansion. And you know, V of t is nothing but P of t into VA of t. Correct, previous expression. So, V naught of t is equal to P of t into VA of t. What is VA of t? So, VA of t, we know it as AC cos 2 pi FCT plus M of t, or cos, what is 2 pi fc? How we can write it in omega ct. Okay, AC cos 2 pi fct, or we can write it as omega ct plus m of t. Okay, so now I will substitute my p of t expression in this equation. So let me say this is equation 1, this is equation 2. So now I will substitute equation 1 into equation 2 and I will solve it. Okay, and you know, this V naught of t is given as an input to your band pass filter. Okay, so band pass filter is designed in such a way that it will allow only fc and fc plus fm, fc minus fm, because the bandwidth is 2fm. So bandwidth is 2fm. So this is a double sideband full carrier. So This V naught of t signal is passed through a bandpass filter. That bandpass filter will remove unwanted components and it will pass only components with frequencies FC. Let us say I'll write it here. FC, comma FC plus or minus FM. So this should be your pass band of your bandpass filter. Okay. So we will find V naught of t and we will pass it through bandpass filter and remove unwanted component. That is the output of your bandpass filter is nothing but double sideband full carrier. Okay. So substituting 1 and 2. So we have V naught of t is equal to AC cos omega ct plus m of t into 1/2 plus, I'm just multiplying my Fourier series bracket terms. So cos omega ct minus 2 divided by 3 pi cos 3 omega ct. Okay. Okay. So I'm just cross multiplying this and I'm solving it. That's all. So AC cos omega ct divided by 2 plus 2AC 2 by pi AC cos omega into cos omega is cos square omega ct. Okay. Okay. Minus 2AC divided by 3 pi cos omega ct multiplication cos 3 omega ct. Okay. Plus m of t by 2. Okay. Plus 2 by pi cos omega ct m of t. Okay. Minus 2 divided by 3 pi m of t cos 3 omega ct. Okay. So I'm just cross multiplying this. Okay. So this is nothing but V naught of t. So this V naught of t is passed through a bandpass filter. Correct or not? Passed through a bandpass filter, and you know the characteristics of bandpass filter is this. The center frequency is FC, FC minus FM, FC plus FM. The reason is you want to produce a double sideband full carrier. Okay, this is your bandpass filter. Okay, so let me examine this. See, AC cos omega ct by 2. What is your frequency present? FC. Okay, and m of t. What is your frequency content present? FM. Okay, okay. 2 AC by pi cos square omega ct. So we have solved a similar example in square law modulator. So cos square omega ct means it is 2fc. So I have derived it. How was it 2fc? Refer it. And here cos omega c, cos 3 omega c. So cos a, cos b. What is your formula? Cos a plus b, cos a minus b. So cos a plus b means omega c plus 3 omega c. What is that? 4 omega c and 3 omega c minus omega c. So you will have 2 omega c. Okay. Or it is, we have considered here in terms of f. So it will become So it will become 4fc and 2fc. Okay. So this is your frequency component in this term. In this term, okay, we will take it later. Here m of t into cos 3 omega ct. So m of t, if it is omega m, so you all know, if we assume m of t as cos theta. So if I assume m of t as cos omega mt into cos 3 omega ct. So what frequencies you have? Cos A, cos B. So cos A plus B, cos A minus B. So cos omega m plus 3 omega c. So omega m means Fm plus 3fc, then Fm minus 3fc. So Fm plus or minus 3fc is a frequency of this term. Okay. See, this is very simple. We have solved the same similar kind of expression in square law modulator. So the same thing I'm using it here. Very simple. M of t, instead of M of t, I'm assuming, you know, M of t is what? Message signal. So M of t is nothing but cos omega mt. So cos omega mt into cos 3 omega ct. It is of the form cos a cos b. So cos a cos b means cos a plus b plus cos a minus b by 2. So Fm uh, omega m plus 3 omega c. If I write in terms of Fm, it is Fm plus or minus 3 fc. Okay. This term 2 by pi cos omega ct m of t. Okay, if I substitute m as, what is your equation for m? If I substitute m as cos omega mt, what is your expression? Cos a cos b. So omega c plus or minus omega m. So if I write it in terms of fc, it is fc plus or minus fm. Okay, so these are the frequency component present in each of these signals. So omega ct, that is your first term, it is fc. For this it is 2fc. For this third term it is 4fc and 2fc. And here it is fm. Here it is fc plus or minus fm. Here it is minus fm plus or minus 3fc. Okay, and you know that band pass filter will allow only what frequency component? It will allow only fc and fc plus or minus fm. So you'll have this frequency component and this frequency component alone in your output of your band pass filter. So you'll have only two frequency component. Okay, so my v naught of t, or not, it is not v naught of t, it is vam of t, because the output of your band pass filter is vam of t. Correct. So vam of t will have only two components. What are those? AC cos omega ct divided by 2 plus 2 by pi cos omega ct into m of t. So if I simplify this further, so v naught of t, you have what? AC cos omega ct divided by 2 plus 2 by pi m of t cos omega ct. Am I right? 2 by pi cos omega ct, AC cos omega ct by 2. Okay. So now if I take AC by 2 common, I will have what? 1 minus 4 m of t by pi into 1 divided by AC into cos omega ct. So I'm just taking AC, this first term as a common term. So AC by 2 cos omega ct. So if I take 1 minus 4 m of t by pi, 1 divided by AC. So this is a simple simplification. Okay. So I can write this as V naught of t is equal to AC by 2 into 1 minus Ka into m of t into cos omega ct, provided that Ka is nothing but 4 divided by pi AC. Okay, I'm replacing this 4 by pi into 1 by AC as Ka. So you will have V naught of t as AC by 2 1 minus Ka into m of t cos omega ct. So this expression, if I simplify this expression, what is that? V naught of t is equal to AC by 2 cos omega ct, okay, minus Ka into m of t cos omega ct. Okay, so further, if I simplify AC by 2 cos omega ct, if I substitute Ka as cos omega mt. Okay, cos omega ct. So what is this? This is nothing but carrier. Correct? This is nothing but cos A cos B. So cos A plus B cos A minus B. So you will have FC plus or minus Fm. So this is what? Sideband, upper sideband and lower sideband. So your output is having two terms. What are they? Carrier and upper sideband and lower sideband. So what is that called? That is called double sideband full carrier. So you can use a switching modulator to generate a double sideband full carrier. Okay, so our aim was to generate a double sideband full carrier, and hence we have derived we have achieved double sideband full carrier using the switching modulator technique. Okay, so clear. So this expression I'm saying it as double sideband full carrier. Okay, this is nothing but double sideband full carrier. Okay. So if you derivation is sufficient till this. So when it is asked in your exam, you can derive till this. Okay, and you can say V naught of t is the double sideband full carrier equation. Okay, henceforth you are able to derive double sideband full carrier using switching modulator. Clear? So in this lecture we have expressed how to derive your equations for double sideband full carrier using switching modulator, or how a switching modulator can be used to derive double sideband full carrier. The logic is it is based on the switching characteristics of your diode. Okay, your carrier is governing the input to your diode. If your carrier is positive, your input is also positive. If your carrier is negative, your input is negative. So when carrier is positive, the diode is forward biased. When the carrier is negative, your diode is reverse biased. So during your forward bias, V naught of t is equal to dA of t. During your negative or reverse biased, V naught of t is equal to 0. So to derive, so this is a kind of periodic, because you have a positive half cycle and negative half cycle in a sine wave. So to equate this, we are relating it with help of a periodic square wave, and we are using the expression for periodic square wave in terms of Fourier series, and we are solving the equations. Okay, and at last you will get V naught of t. This V naught of t is passed through a bandpass filter with Fc plus or minus Fm as its frequency, passband frequency. So when you filter the unwanted components, you will get the original DSB Fc. So this is how we can derive DSB Fc using switching modulator. Okay, I hope you understood. Okay, so thank you.